please pause the video and try this problem. And as you are trying this problem, I hope that you will be trying to apply the systematic process for Newton's second law problems, which we introduced in the previous video. Okay, now let's discuss the solution to this problem together. Remember that if you find that this video explanation moves too slowly, you can use these solutions documents to supplement or replace the video explanation. And remember that if you like, you can use the table of contents to skip to the particular parts of the video that cover the particular parts of the solution that are giving you difficulty. Here on the screen is a summary of the solution. We start by choosing a problem-solving framework. The problem mentions the concepts of mass, force, and acceleration, which can be substituted into the Newton's second law equations. So we will apply the Newton's second law problem-solving framework for this problem. Notice that this problem is an inclined plane problem, but we do not say that we're going to apply an inclined plane problem-solving framework. There is no separate problem-solving framework for inclined planes. Instead, we can solve an inclined plane problem using the same Newton's second law problem-solving framework that we already introduced in the previous video. Here again is the handout containing the systematic step-by-step process for Newton's second law problems, which we demonstrated in the previous video. I hope that you have this handout printed out so that you can follow along with the steps as we demonstrate them in this video. Make a note of what the question is asking us for. The question is asking us for the magnitude of the normal force. The question is asking us for the direction of the normal force. The question asks for the magnitude of the acceleration and for the direction of the acceleration. The problem says that the box is sliding down the hill. So we draw the velocity vector pointing parallel to and down the hill to indicate the object's direction of motion. Check that all the given units are SI units. Well, yes, kilograms are the SI units for mass. Next, we work on the free body diagram. The problem mentions the mass of the box, and that's a clue that we should draw a free body diagram showing all the forces on the box. We start by drawing the weight force on the box, and then we ask ourselves, what are the things that are touching the box? Well, the box is being touched by the hill. The hill is basically an inclined plane, and an inclined plane is the type of thing that we treat as a surface, which means that the hill is going to be exerting a normal force on the object. Whenever a surface exerts a normal force, you should automatically check whether the surface also exerts a frictional force. But we know that there's no friction from this surface because the problem told us the hill is frictionless. Are there any other forces on the box? Well, ask yourself, is there anything else that is touching the box besides the hill? No, nothing else is touching the box, so there are no other forces to include in the free body diagram for the box. We use these rules to determine the directions of the forces. The direction of the weight force is always straight down, so we draw a downward vector for the weight force. Notice that for determining the direction of the weight force, it makes no difference that this object is on the surface of an inclined plane. The direction of the weight force is always straight down. Now, the direction of the normal force should be perpendicular to and away from the surface that is touching the object. So the direction of the normal force exerted by the surface of the hill on the box should be perpendicular to and away from the surface of the hill. Well, that would be this direction. This direction. So here is the direction of the normal force pointing perpendicular to and away from the surface of the hill. In this free body diagram, we represent the surface of the hill with this dashed reference line. In the previous problem in this video series, the normal force pointed up. But I hope that didn't give you the idea that the normal force will always point up. Don't assume that the normal force points up. There are many situations where the normal force does point up, like the previous problem, but there are also many situations in which the normal force does not point up, such as this problem. Use this rule to determine the direction of the normal force. Now we work on the force table. In the first row of the force table, we represent the magnitudes of the overall force vectors. We are not given a value for any of the magnitudes of any of the forces on this problem, but we do have a special formula for finding the magnitude of the weight, and we use that to find that the magnitude of the weight is 39.2 newtons. There's no special formula for finding the magnitude of the normal force, so we represent the unknown magnitude of the normal force with the symbol little n, written without an arrow on top to indicate that this symbol stands just for the magnitude of the normal force. In our force table, we do not try to figure out how these forces will interact with each other. We're going to let the Newton's second law equations figure out those interactions for us later in our solution. Before we work on the components, we must choose our axes. We should usually choose an axis that points in the object's direction of motion. The box is moving parallel to and down the surface of the hill. So I'm going to choose a positive x-axis that points parallel to and down the surface of the hill. Then we'll choose a y-axis that points perpendicular to the surface of the hill. Notice that these axes are quite different from the axes we chose for the previous problem, where the object was moving along a horizontal surface. Make sure you actually write down the axes that you've chosen, because these axes will be crucial for breaking the forces into components. Now we can start breaking the forces into components. Let's begin by working on the components for the normal force. Now our normal force vector points parallel to the y-axis, which means we can apply this rule. Well, our normal force vector is pointing in our positive y direction. So the y component of the normal force will be positive, and the magnitude of the y component will be the same as the overall magnitude, represented by little n, and the other component, the x component, is 0. What about the components of the weight force? Well, the weight force vector is neither parallel nor antiparallel to either of these axes that we've chosen. The weight force vector is at a slant to both of our chosen axes, so we cannot apply this rule. Instead, we are going to have to draw a right triangle and use the SOHCAHTOA equations in order to break the weight force into components. It should be boringly easy for you to break the weight vector into components for an inclined plane problem. So I'm going to discuss the steps for that process in some detail. Of course, if it is already boringly easy for you to break this weight vector into components, you could use the table of contents in the progress bar to skip ahead to the next part of the solution. Here is the right triangle that we're going to use to break the weight vector into components. Students often have difficulty drawing the correct right triangle. We can use this rule to draw the correct right triangle. So in our right triangle, the hypotenuse should represent the overall vector, and that's what we have here. This side is the hypotenuse of this right triangle because it's across from this 90-degree angle, and this side does represent the overall downward pointing weight vector. Now, this is the key. The legs of your right triangle should be parallel or anti-parallel to the axes. So here I've drawn the leg for the x component of the weight parallel to the x-axis. And here I've drawn the leg for the y component of the weight parallel to, or anti-parallel to, the y-axis. Notice how the legs of this right triangle are parallel or anti-parallel to our axes. Students often draw this right triangle incorrectly. For example, students often wrongly try to draw the right triangle for this problem like this. Can you see why this right triangle is wrong? One way that you can see that this is wrong is that the legs are not parallel to the axes. It's tempting to draw a right triangle with horizontal and vertical legs, since that's the type of right triangle that we used in the previous video. But horizontal and vertical legs are not appropriate for this problem, because for this problem, our axes are not horizontal and vertical. So we can see that this right triangle is wrong because the legs are not parallel to our axes. Now you can see why it's so important to write down the axes that you're using for each problem. The components are based on the axes. Now we have to draw arrows on the components to represent their directions. We can use this rule. The head of a component arrow should be at the head of the overall vector, and the tail of a component arrow should be at the tail of the overall vector. So in this location, we see the head of the overall weight vector, and so at that same location, I'll draw the head of this y component. In this location, we see the tail of this overall weight vector, so here I'll draw the tail of this x component, which means that this must be the head of the x component. We need to draw the directions of the components so that we can figure out the plus or minus signs on the components. W sub x is pointing in our positive x direction. So I'll say that W sub x is positive. W sub y is pointing in our negative y direction. So I'll say that W sub y is negative. It's a good idea to figure out the plus or minus signs on the components before you figure out the magnitudes, because if you figure out the magnitudes of the components first, you're more likely to forget about the signs altogether, and then you might not notice this crucial negative sign. Now, we would like to start figuring out the magnitudes of these components. In order to do that, we need to apply the SOHCAHTOA equations, but we're not ready yet to apply the SOHCAHTOA equations to this right triangle. We cannot apply the SOHCAHTOA equations to this right triangle until we have determined an angle inside the right triangle. Of course, we know that this angle is 90, but we have to determine at least one of these other angles before we can apply the SOHCAHTOA equations to this right triangle. Of course, we already know this angle, but so far, we haven't determined either of these angles. To correctly apply the SOHCAHTOA equations, you need to be using an angle inside the right triangle. We can't correctly apply the SOHCAHTOA equations focusing on this angle outside the right triangle. Here is one way to do that. What I've done here is I've taken this line, this vertical line for the weight vector, and I extended it downwards a little bit. And I took this horizontal dashed line and extended it leftwards a little bit so that we can form a large right triangle. Now I formed the large right triangle ADE. I formed the large right triangle ADE, which I've now highlighted in color. Also, I've given the angles names to make them easier to think about. Let's call this 30-degree angle theta. Let's call this angle, which we don't know yet, alpha, and this angle, which we don't know yet, beta. Now we're going to use the geometry fact that the acute angles in a right triangle add up to 90 degrees. Well, alpha and theta are the acute angles in this large right triangle outlined in color. So alpha plus theta must add up to 90 degrees. And since we already know that theta is 30, that means that alpha must be 60 degrees. This rule should make good sense to you because if the acute angles add up to 90 and then you add in the right angle, you'll get a total of 180 degrees. And we know that the total of all three angles in a right triangle should indeed be 180 degrees. So now we've figured out that this angle, alpha, is 60 degrees, and we should label that in our diagram. Now, we could apply the SOHCAHTOA equations now. We could apply the SOHCAHTOA equations focusing on this 60-degree angle, but it would be more conventional to focus on angle beta. So let's go on and determine angle beta. In order to determine angle beta, let's shift our attention to this smaller right triangle. Now we're going to shift our attention to the smaller right triangle that I've now labeled in color, right triangle ABC. Well, in this new right triangle, the acute angles are alpha and beta. So we know that alpha and beta add up to 90 degrees using this rule. The acute angles are the angles that are less than 90 degrees, by the way. Now we've already figured out that alpha is 60 degrees, and that tells us therefore that beta must be 30 degrees. So now we know this angle is 30 degrees, and we should add that to our right triangle. Now we know that this angle, beta, is 30 degrees. As you are going through this process, draw a large sketch with a large right triangle. If you draw a small sketch with a small right triangle, you won't have enough room to include all the labels and details that you need to think clearly about the situation and about the geometry. When you're doing geometry, draw large diagrams so there's plenty of space to make clear labels for all the features of your diagram. And plenty of space to add new information when you figure it out. Like we added the information about the size of this angle and the size of this angle when we figured those out. Now that we know the angles inside this right triangle, we can apply the SOHCAHTOA equations. Now first we have to decide which of these two angles we're going to focus on in our SOHCAHTOA equations. Are we going to focus on the 30-degree angle or the 60-degree angle? It would be perfectly fine to focus on either of those two angles, but the conventional choice is to focus on this 30-degree angle because it equals the angle that we were given. Since we were given an angle of 30, it's more conventional to focus on the 30-degree angle inside this right triangle. So I'm going to draw an asterisk here on the 30-degree angle to indicate that that's the angle we're focusing on. You can see that I'm focusing on this 30-degree angle in the SOHCAHTOA equations because I'm taking the sine and cosine of 30 degrees. Now we label the sides of the right triangle as hypotenuse, opposite, and adjacent sides. This side is the hypotenuse because it is across from the 90-degree angle. It might seem weird to have a vertical hypotenuse, but that's what we have in this right triangle. This is a right triangle with a vertical hypotenuse. Now this side gets labeled as adjacent because this is the leg that is adjacent to the 30-degree angle that we decided to focus on. And this leg gets labeled as opposite because this leg is opposite to the 30-degree angle that we decided to focus on. Now we can see that the length of the opposite side will measure the magnitude of the x component of the weight, and the length of the adjacent side will measure the magnitude of the y component of the weight. And the length of the hypotenuse measures the magnitude of the overall weight vector, 39.2 newtons. We use the special formula W equals mg to determine the magnitude of the overall weight vector, 39.2 newtons. So we label the length of this hypotenuse as 39.2 newtons, and we can substitute that here in our SOHCAHTOA equations. Then we can solve the SOHCAHTOA equations for the magnitudes of the components. Why am I using absolute value symbols in the SOHCAHTOA equations? We use absolute value symbols in the SOHCAHTOA equations to indicate that the SOHCAHTOA equations only tell us the magnitudes of the components. So by this point, from our algebra, at this point we've only determined the magnitudes of the components from our algebra. We determine the signs, plus or minus, of the components in a separate step. Actually, we had earlier determined the plus or minus signs, so now we can just add that to the value of the components in this second step. We already decided that w sub x is positive, and we already had decided that w sub y is negative, because w sub y is pointing in our negative y direction. W sub x is pointing in the positive x direction. In this line, I'm using absolute values to indicate that this line of the work only indicates the magnitudes of the components. And in this line, I'm writing the symbols without the absolute value signs to show that this line represents the complete components, including both their magnitudes and their plus or minus signs. It's crucial to include this negative sign. If we leave out this negative sign on w sub y, we're going to get the problem wrong. Remember that I recommend that you should include a plus sign in front of all of your positive components, because that will make you more likely to notice when you need a negative sign in front of negative components. It should be boringly easy for you to break vectors into components, including for inclined plane problems. It should be boringly easy for you to go through the process we just went through of breaking the weight vector into components for an inclined plane problem. So you should carefully study that process that we just went through and practice that process until it is boringly easy for you. It's interesting to compare the process that we used for breaking the weight force into components for this problem with the process that we used for breaking the tension force into components in the previous problem. Notice that for this problem, we used sine for the x component and cosine for the y component. But notice that in contrast, for the previous problem, we used sine for the y component, not the x. And in the previous problem, we used cosine for the x component, not the y. The moral is that you should not assume that you're going to be using sine or cosine for the x or the y component for any particular problem. Instead, you should go through the SOHCAHTOA process, which will determine for you, for each problem, whether you should be using sine or cosine for the x or y component for that problem. The key is to label the angle in the right triangle which you're focusing on with an asterisk, and then correctly label the adjacent and opposite legs in the right triangle. In this problem, the adjacent leg represented the y component. So for this problem, we used cosine to determine the magnitude of the y component. But in the previous problem, the adjacent leg represented the x component. So for the previous problem, we used cosine to determine the magnitude of the x component. And now we can take our results for the components and substitute them into the force table. Now that the force table is finished, we can work with our Newton's second law equations. We write a Newton's second law equation for the x component and a Newton's second law equation for the y component at the top of two adjacent columns. The sigma symbol tells us to add the individual force components on the left sides of the equations. We get those components from our force table. So here we add 19.6 plus 0, and here we add negative 33.9 plus n. Be careful to include this crucial negative sign when you're adding this component. The box is moving parallel to and down the hill. The box has no motion perpendicular to the hill. That means that the box is moving in the x component. The box has no motion in the y component. Since the box is motionless in the y component of the acceleration is 0. So we can substitute 0 for a sub y in our Newton's second law y equation. There's no reason to think that a sub x is 0, so we'll simply continue to use the symbol a sub x for a sub x. We can see now why it was helpful for this inclined plane problem to choose an x-axis which is parallel to the incline. The main reason why these axes are helpful for this problem is that they allow us to substitute 0 for a sub y. If we had chosen horizontal and vertical axes for this problem, then we would not have been able to substitute 0 for either a sub y or a sub x. So, if we had chosen horizontal and vertical axes for this problem, the problem would have been substantially more difficult to solve. Both of the equations now have only one unknown, so it's not difficult to solve each of these equations for the unknown in that equation. Now, we can answer the question. Here, we determined that the magnitude of the normal force is 33.9 newtons, which I'll round off to 34 newtons. And here, we determined that the direction of the normal force could be described as perpendicular to and away from the surface of the hill. We also have to answer the magnitude and direction of the acceleration. Well, we've determined that a sub y is 0, and that a sub x is positive 4.9 meters per second squared. This acceleration mathematically came out to be positive, and we've discussed that it's a good idea to include plus signs in front of positive components, so I've done that here. Now, since the y component of the acceleration is 0, the magnitude and direction of the overall acceleration will be the same as the magnitude and direction of the x component. Well, a sub x is pointing in the positive x direction, and our positive x direction is parallel to and down the hill. So that's the direction of the acceleration, and a sub x has a magnitude of 4.9 meters per second squared, which is the magnitude of the acceleration. And now here I've drawn the overall acceleration vector in the main sketch to indicate that we discovered that the direction of the overall acceleration is parallel to and down the hill. Check to make sure that you include units on your answer. Check to make sure that you've answered the right question and that you've answered all parts of the question. Don't just answer the magnitudes of the normal force and acceleration. Make sure that you also answer the directions of the normal force and acceleration. Check to make sure that your results make sense. It makes sense that this result for little n came out to be positive. The symbol little n written without an arrow on top stands for the magnitude of the normal force. Magnitudes can never be negative, so it makes sense that this result came out to be positive. To understand why the size of this result makes sense, let's use this version of the free body diagram, where the weight force is broken into components. Earlier in our solution, we determined that w sub x points parallel to and down the hill, and w sub y points perpendicular to and into the hill. So in this version of the free body diagram, I've drawn w sub x pointing parallel to and down the hill, and w sub y pointing perpendicular to and into the hill. Now we can see that our result for the magnitude of the normal force came out to equal the magnitude of w sub y. They're both 33.9 newtons. Why does that make sense? Well, w sub y is trying to begin the box moving into the surface of the hill. To prevent the box from being dragged into the surface of the hill, w sub y has to be canceled by the normal force. So it does make sense that the magnitude of the normal force equals the magnitude of w sub y. Our result demonstrates that you should not assume that the magnitude of the normal force will equal the magnitude of the weight. Sometimes they are equal, but there are other problems, such as this one, where they are not. In this problem, the magnitude of the normal force doesn't equal the magnitude of the weight. Instead, the magnitude of the normal force equals the magnitude of the y component of the weight. Don't make an assumption about the normal force. Just use the Newton's second law equations to determine the magnitude of the normal force. Now let's ask whether our result for a sub x makes sense. Does it make sense that our result for a sub x is positive? Well, according to Newton's second law, the direction of the net force should determine the direction of the acceleration. The only force in the x component for this object is w sub x. W sub x is pointing parallel to and down the hill. Therefore, the net force for the x component will point parallel to and down the hill. Therefore, the x component of the acceleration will point parallel to and down the hill, and that is our positive x direction. So yes, it does make sense that a sub x came out to be positive. The object is accelerating down the hill because w sub x is pulling down the hill. Now, what about the magnitude of this result? Why does that make sense? Well, for this problem, it is interesting to compare our result for a sub x with free fall acceleration, 9.8 meters per second squared. Notice that the magnitude of our result is less than free fall acceleration. Why does that make sense? Does it make sense that our result is less than free fall acceleration? Well, free fall acceleration, 9.8 meters per second squared, is the magnitude of the acceleration that would be obtained from the full force of the weight. But on this problem, a sub x is not being generated by the full force of the weight. A sub x is being generated only by the x component of the weight. Since a sub x is generated only by the x component of the weight rather than by the full weight, it makes sense that the magnitude of a sub x is less than the magnitude of free fall acceleration. Remember that free fall acceleration is what you get when the only force on the object is the force of the Earth's gravity, which means that the only force on the object for free fall is the weight force. You could also just use basic common sense intuition. Your basic common sense about the real world should tell you that if one object is being dropped in free fall and another object is being allowed to slide down a hill, the object that is dropped in free fall will fall with a greater acceleration than the object that is sliding down the hill. So we can see that yes, the magnitude of this result does make sense. The main difference between this problem and the problem in the previous video is that this problem involves an inclined plane. So what was especially important for us to be able to solve this inclined plane problem? Well, I think the most important part about an inclined plane problem is to think in terms of components and to think correctly about the components for the problem. We determined that the weight of this box was 39.2 newtons. Where did we substitute the 39.2 newtons into our Newton's second law equations? Answer: we did not substitute 39.2 newtons into the Newton's second law equations. Instead, we used SOHCAHTOA to break the 39.2 newton weight force into components, and then we substituted the x and y components of the weight into our Newton's second law equations. Remember that to think about the components clearly, you must choose and write down the axes that you are using. For this inclined plane problem, where the object was moving parallel to the incline, it made sense to choose a positive x-axis pointing parallel to the incline in the object's direction of motion. Then we used those axes to draw the right triangle that we used to break the vector into components. We drew a right triangle whose legs were parallel to our axes. We used geometry to go from this angle, which is outside the right triangle, to figure out the angles inside the right triangle. And then we were able to apply SOHCAHTOA to figure out the components. Make sure that it is boringly easy for you to break the weight vector into components for an inclined plane problem. Here's another respect in which you have to think in terms of components. Notice how we think quite differently about the x component of the acceleration and the y component of the acceleration. Notice that although this is an inclined plane problem, we don't need a brand new problem-solving framework for solving an inclined plane problem. We can solve this inclined plane problem using the same systematic method for Newton's second law problems that we introduced in the previous video. We just have to make a few adjustments or adaptations in the method. One important adaptation is choosing a positive x-axis that points in the object's direction of motion, which in this case is parallel to and down the incline. We have to use those axes to correctly break the weight force into components. Other than that, the approach for an inclined plane problem is quite similar to the approach for any other Newton's second law problem. Always try to use the exact right symbol, including the exact right subscripts. Notice how we carefully used x and y subscripts to distinguish our Newton's second law equation for the x component from our Newton's second law equation for the y component. You can't think clearly about the components unless you're using subscripts to clearly distinguish the x and y components. Here's another way that we tried to use the exact right symbols. We used absolute value signs in our SOHCAHTOA process to distinguish between the magnitudes of the components and the complete components. When we write w sub x and w sub y in absolute value signs, they stand just for the magnitudes of the components. But when we write those symbols without the absolute value signs, they stand for the complete components, including plus or minus signs. We can see that having a separate symbol just for the magnitude of the components was helpful to us here, because by using the absolute value signs in our SOHCAHTOA equations, we were able to remind ourselves that the SOHCAHTOA equations only tell us the magnitudes of the components. It was our job to add the plus or minus signs to the components in a separate step based on the directions of the components in our right triangle. Remember that if we don't include this minus sign on w sub y, we're not going to substitute the correct number into this position in the Newton's second law equation, and we're going to get the wrong answer. So it really is helpful to have symbols that remind ourselves that it is our job to figure out the plus or minus signs on the components in a separate step. If you found this problem to be challenging, then I would recommend that before you try the next problem, it would be better to take a blank piece of paper and try this same problem again from scratch to make sure that you've actually mastered the techniques that we're talking about in this video. When you feel that you have mastered the techniques we covered in this video, then you can move on to the next video in the series, which will give you additional practice with another inclined plane problem. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.